Alright, welcome to video lecture 1, wave properties. Please make sure that these notes are in your interactive notebook, page 103. Moving right along. So, our first question is, what is a wave? Well, there's a lot of different ways of thinking about waves and of describing waves. The one that we are going to use is the transfer of energy through a medium by causing oscillation in the medium. Alright, so that's a lot of stuff, so let's start at the beginning. A transfer of energy. We know what energy is. Specifically, we're talking kinetic energy. We're moving this kinetic energy through a medium. Medium is a fancy term for stuff, through some sort of material. Now we're going to do that by causing oscillation. All that stuff that we've been talking about. Remember, oscillation is something moving back and forth or up and down at a nice constant rate or frequency. Well, if something over on one side starts oscillating, due to frictional forces, it'll cause the thing next to it to start oscillating, which causes the next thing to start oscillating, which causes the next thing to start oscillating, which causes the next thing to start oscillating, and so on, until you get everything oscillating, except they don't all oscillate at the exact same time. They're not all up at the same time or all down at the same time. Since there's that friction, there's a little bit of a delay. So this one goes up, and a little bit later, this one comes up. So you end up with this pretty little shape. More on that shape in a moment. So they cause oscillation, which means everything that we've been learning about in this last unit, we're learning about now. They have displacement, they have amplitude, they have frequency, and they have period. So, in case you don't remember what those things are, displacement is the distance from where they want to be, equilibrium. So, on a spring, that was, well, where is it now? What is the distance between there and the equilibrium point of the spring? The equilibrium point is flat. Whatever the material is, it wants to be flat. It wants to be perfectly horizontal. It wants to be happy. It wants to be in its normal spot. We are displacing it from that using oscillation, which means, of course, that it has an amplitude or a maximum displacement, and it's oscillating at a nice irregular rate or frequency. How often a cycle happens? Remember, that's measured in cycles per second or hertz, which means it also has a period, or how much time one cycle takes, measured in seconds per cycle. Alright, so all this stuff is for oscillation, but it's also true for a wave, because anything that oscillation is doing is also happening in a wave. The big difference between oscillation and waves, though, is that where oscillation is just happening in time, it's going up and down and up and down and up and down and up and down as time goes on. Waves are moving up and down and up and down and up and down as time goes on, but they're also moving forward. So they also have this thing called wavelength. Now, wavelength has this nifty symbol, Greek letter lambda. So whenever I say what is the lambda of something, where I use the symbol, I am talking about the wavelength of that object. So the definition of wavelength is the length of one cycle. All right, what does that mean? So I'm talking about the distance between 2 points at the same part of the cycle. For instance, top of the cycle to top of the cycle. This distance here would be my wavelength. Yay, wavelength. Next. So we have 3 different types of waves. We are only going to talk about 2. They all look very similar, but they are very, very different in what causes them to happen. So the first is a water wave. You can see this nice dark blue line. It shows you exactly what you would expect a water wave to look like. We're not talking about breaking waves. We're talking about just you're out on the ocean or on a lake, and there are some ripples. This is a weird kind of wave, because if you look at what's below it, it's showing that little particles of water are not moving up and down and up and down. nor are they moving left, right, left, right, left, right. They're doing both at the same time. They're making these funny circle patterns. So if you follow the blue dot, you see that it starts at the top of the circle, here. Then it's at 3 o'clock. Then it's at 6 o'clock. Then it's at 9 o'clock. Then it's up at 12 o'clock again. It is moving through the circle. And if you get that through space and time, you get this lovely wave pattern that we're used to seeing. So, we're not going to talk about water waves that much. Transverse waves, we are. Transverse wave looks exactly the same, except there's no forward-back motion. There's no circular motion. It's just straight up, straight down. Where we call the very, very tippy top of the wave the crest, and the bottom the trough. All right, so now below that I have a bunch of particles. You can follow one black line as it goes down, back to equilibrium, then down to the bottom, then back up to equilibrium, then up, then back to equilibrium. It's exactly what a horizontal spring is doing, or a vertical spring is doing, or a pendulum is doing. And if you have this happening through space as well as time, you get this lovely little curve shape, where right here is equivalent to a crest, and right here is equivalent to a trough. Yay, transverse waves. These would be waves on things like strings or earthquakes. All right, now you have longitudinal waves. These would be sound waves. Pretend that each vertical line here represents a piece of air. Now this is hard because we don't really see longitudinal waves, so bear with me. You can see how all of the lines are squished together, then they're spread apart, then they're squished together, then they're spread apart, then they're squished together, then they're spread apart, then they're squished together, so on. We call the squished together bits compressions, and they are like crests. We call the spread out bits rarefactions, and they're like the trough. So if you look below that, you can follow one dot and see that it starts all the way at the left, then it's halfway to the middle, then it's at the middle, then it's halfway to the right, then it's at the right, then it's halfway to the middle, then it's at the middle, halfway to the left, it's at the left. As it makes that oscillation back and forth and does it through space and time, you get a compression. Hey, check that out right there. They're all nice jam-packed in close to each other. And you can get a rarefaction. Oh, hey, you mean like right here where they're all spread out. Now, maybe you don't believe me. Maybe there's too many lines. It's hard to tell. Let me get rid of them. See? Closely packed together, spread apart, even though all they're doing is moving to the left and to the right. All right, so now, how would we label these waves? All right, well, let's have a transverse wave. All right, now, t is the x-axis here, and y is the y-axis. Y is our displacement. T is time. All right, so knowing that, that means that this and this right here, these are both the amplitude. Now, come on, select color. Here we go. This distance from here to there, or from the top to the top, this would be the period. All right, now, down below here, we no longer have time, we have x. So this is measured in space. So we have slightly different looking graph. Very similar, but slightly different. Again, this is still the amplitude, that is still the amplitude. But this length is not the period, because we're not measuring it in time. We're measuring it in space. Which means this is our wavelength, as is that. The length of the wave is the wavelength. How much time the wave is the period. All right, now, well, what would a longitudinal wave look like, though? How would we graph that? Well, I'm going to make this easy for you. That was not the button I meant to push. I wonder where my stuff went. It's a mystery. Hold on. All right, not entirely sure what happened there. All right, let's make it easy for you. Exactly the same. Where y is still the displacement, but instead of vertical displacement from where it wants to be, it is the horizontal displacement from where it wants to be. Yay! Distance from the red dotted line. So it looks exactly the same. Not going to draw it again. Last thought, but wait. If there is a wavelength, wavelength, and if there's a period, period, then there must be a speed. How so, Mr. Saslow? Well, wavelength, that's like delta x. Period, well, that's, time. And the old equation for speed is delta x over delta t. Which means we get a brand new equation for our wave. Wave speed is going to equal our length divided by our time. Except 1 over period, that's our definition. Just right here. That's a definition of frequency. So, wave speed equals wavelength times frequency. Where it is important to note that the only thing that determines the speed of the wave is the medium that it travels through. It doesn't matter how big the amplitude is, or how big the period is, or what the wavelength is. The thing that determines the speed is the material. And this just happens to give us the mathematical relationship between those things. All right, that's it. Congratulations, you survived.